Click the link on description that will open page like this. Here click on Song by Genre. It consists of dataset and IPYNB file. Happy coding. Please subscribe to my channel. Your single subscription will make my day. Hello everyone. In this project we are going to classify songs based on their genre from audio data. While listening to a music in any digital music streaming service, you may be wondering, these recommendations are so on point. How does this playlist know me so well? Over the past few years, streaming services with huge catalogs have become the primary means through which most people listen to their favorite music. But at the same time, the sheer amount of music on offer can mean users might be a bit overwhelmed when trying to look for newer music that suits their tastes. For this reason, streaming services have looked into means of categorizing music to allow for personalized recommendations. One method involves direct analysis of the raw audio information in a given song, scoring the raw data on a variety of metrics. Today, we'll be examining data compiled by a research group known as the Echo Nest. Our goal is to look through this dataset and classify songs as being either hip-hop or rock, all without listening to a single one ourselves. In doing so, we will learn how to clean our data, do some exploratory data visualization, and use feature reduction towards the goal of feeding our data through some simple machine learning algorithms, such as decision trees and logistic regression. To begin with, let's load the metadata about our tracks alongside the track metrics compiled by the Echo Nest. A song is about more than its title, artist, and number of listens. We have another dataset that has musical features of each track such as danceability and acousticness on a scale from -1 to 1. These exist in two different files, which are in different formats, CSV and JSON. While CSV is a popular file format for denoting tabular data, JSON is another common file format in which databases often return the results of a given query. Let's start by creating two pandas data frames out of these files that we can merge so we have features and labels, often also referred to as X and Y, for the classification later on. Our first task here is, read in the data using pandas and merge the data frames into one usable dataset. Using the pandas read_CSV function, read in the file with the track metadata, dataset/fma-rock-vs-hiphop.csv, and name the data frame tracks. Using the pandas read_JSON function, read in the JSON file with the track acoustic metrics, dataset/etchinist-metrics.json, and name the data frame etchinist_metrics. Set the precise_float argument to true when reading in your data. Merge the data frames on matching track_id values. Only retain the track_id and genre_top columns of tracks. Etchinist_metrics should be the first, left, data frame in the merge. Inspect the data frame using the info method. Data by using head function of pandas data frame. We can see out data frame has track_id, acousticness, danceability, energy, instrumentalness, liveness, speechiness, tempo, valence, genre top as columns. Let's see pairwise relationships between continuous variables. We typically want to avoid using variables that have strong correlations with each other, hence avoiding feature redundancy, for a few reasons. To keep the model simple and improve interpretability, with many features, we run the risk of overfitting. When our datasets are very large, using fewer features can drastically speed up our computation time. To get a sense of whether there are any strongly correlated features in our data, we will use built-in functions in the pandas package. Our next task is to explore correlations in our dataset using pandas core function. Visually inspect the correlation table generated from data frame core for any strong correlations. The feature data. As mentioned earlier, it can be particularly useful to simplify our models and use as few features as necessary to achieve the best result. Since we didn't find any particular strong correlations between our features, we can instead use a common approach to reduce the number of features called principal component analysis, PCA. It is possible that the variance between genres can be explained by just a few features in the dataset. Principal component analysis rotates the data along the axis of highest variance, thus allowing us to determine the relative contribution of each feature of our data towards the variance between classes. However, since principal component analysis uses the absolute variance of a feature to rotate the data, a feature with a broader range of values will overpower and bias the algorithm relative to the other features. To avoid this, we must first normalize our data. There are a few methods to do this, but a common way is through standardization, such that all features have a mean equals 0 and standard deviation equals 1. The resultant is a z-score. Our goal is to prepare our dataset for training a model and standardize the data. Define our features from echo tracks by removing genre top and track id from the data frame using data frame drop along axis 1. Features equals echo tracks drop columns equals genre top track id. Define our labels, in this case, the genre top column from echo tracks. Labels equals echo tracks genre top. Import the standard scalar from the scalar. Preprocessing module from scalar. Preprocessing import standard scalar. Define an instance of the standard scalar called scalar without passing any arguments. Scalar equals standard scalar. Use the fit_transform method to scale features and save to a new variable called scaled_train_features. Scaled_train_features equals scalar.fit_transform features. The next thing to do is to apply principal component analysis on our scaled data. Now that we have pre-processed our data, we are ready to use PCA to determine by how much we can reduce the dimensionality of our data. We can use scree plots and cumulative explained ratio plots to find the number of components to use in further analyses. Scree plots display the number of components against the variance explained by each component, sorted in descending order of variance. Scree plots help us get a better sense of which components explain a sufficient amount of variance in our data. When using scree plots, an elbow, a steep drop from one data point to the next, in the plot is typically used to decide on an appropriate cutoff. Use PCA to determine the explained variance of our features. Import the matplotlib pyplot module as PLT, and our PCA class from scalar decomposition. Define %matplotlib inline. This is just to make plots appear in the notebook. Import matplotlib pyplot as PLT from scalar decomposition. Import PCA. Create our PCA class using PCA equals PCA. Fit the model on our scaled train features using PCA.fit scaled_train_features, and retrieve the explained variance ratio. exp variance equals PCA. Explained variance ratio. Make a scree plot of the variance explained by each component. Fig ax equals PLT. Subplots ax.bar range PCA. N components, PCA. Explained variance ratio, ax.setX label, principal component hash. We run PCA on all our features at first, which is done by default if n_components is not specified. Further visualization of PCA. Unfortunately, there does not appear to be a clear elbow in this scree plot, which means it is not straightforward to find the number of intrinsic dimensions using this method. But all is not lost. Instead, we can also look at the cumulative explained variance plot to determine how many features are required to explain, say, about 85% of the variance. Cutoffs are somewhat arbitrary here, and usually decided upon by rules of thumb. Once we determine the appropriate number of components, we can perform PCA with that many components, ideally reducing the dimensionality of our data. Plot the cumulative explained variance of our PCA. Import the NumPy package as NP. Import NumPy as NP. Calculate the cumulative sums of our explained variance using np.cumsum. cum_exp variance equals np.cumsum exp_variance. Plot the cumulative explained variances using ax.plot and look for the number of components at which we can account for greater than 85% of our variance. Assign this to n components. Fig, ax equals plt.subplots. Ax.plot, cumulative exp variance. Ax.axline, y equals 0.85. Line style equals, n components equals 6. Perform PCA with the chosen number of components and project data onto components. PCA equals PCA, n components, random state equals 10. PCA.fit, scaled train features. PCA projection equals PCA.transform, scaled train features. Perform PCA using n components and project our data onto these components. Next we have to train a decision tree to classify genre. Now we can use the lower dimensional PCA projection of the data to classify songs into genres. To do that, we first need to split our dataset into TRAN and test subsets, where the TRAN subset will be used to train our model while the test dataset allows for model performance validation. Here, we will be using a simple algorithm known as a decision tree. Decision trees are rule-based classifiers that take in features and follow a tree structure of binary decisions to ultimately classify a data point into one of two or more categories. In addition to being easy to both use and interpret, decision trees allow us to visualize the logic flowchart that the model generates from the training data. Here is an example of a decision tree that demonstrates the process of weather. If it is sunny, it will ask how is the humidity, whether it is high or normal. If it is rainy, it will check for how the wind is, whether it is strong or weak, and do the classification. Import train_test_split function and decision tree classifier. Your code. From sklearn.model selection import train test split. From sklearn.tree import decision tree classifier. Then split our data. Train features, test features, train labels. Test labels equals train test split. PCA projection. Labels, random state equals 10. Train our decision tree. Tree equals decision tree classifier, random state equals 10. Tree.fit, train features, train labels. Find the predicted labels of the test features from our trained model using the model.predict notation. Pred labels tree equals tree.predict, test features. Although our tree's performance is decent, it's a bad idea to immediately assume that it's therefore the perfect tool for this job. There's always the possibility of other models that will perform even better. It's always a worthwhile idea to at least test a few other algorithms and find the one that's best for our data. Sometimes simplest is best, and so we will start by applying logistic regression. Logistic regression makes use of what's called the logistic function to calculate the odds that a given data point belongs to a given class. Once we have both models, we can compare them on a few performance metrics, such as false positive and false negative rate, or how many points are inaccurately classified. Import logistic regression. From sklearn.linear model import logistic regression. Train our logistic regression and predict labels for the test set. Logreg equals logistic regression, random state equals 10. Logreg.fit, train features, train labels. Pred labels logit equals logreg.predict, test features. Print the classification reports for our trained decision tree and logistic regression models. From sklearn.metrics import classification report. Class representative tree equals classification report, test labels, pred labels tree. Class representative log equals classification report, test labels, pred labels logit. Then we have to balance our data for greater performance. Both our models do similarly well, boasting an average precision of 87% each. However, looking at our classification report, we can see that rock songs are fairly well classified, but hip-hop songs are disproportionately misclassified as rock songs. Why might this be the case? Well, just by looking at the number of data points we have for each class, we see that we have far more data points for the rock classification than for hip-hop, potentially skewing our model's ability to distinguish between classes. This also tells us that most of our model's accuracy is driven by its ability to classify just rock songs, which is less than ideal. To account for this, we can weight the value of a correct classification in each class inversely to the occurrence of data points for each class. Since a correct classification for rock is not more important than a correct classification for hip-hop, and vice versa, we only need to account for differences in sample size of our data points when weighting our classes here, and not relative importance of each class. Firstly, subset a balanced proportion of data points. Hop only equals echo tracks.lock, echo tracks, genre top, equals. Hip hop, rock only equals echo tracks.lock, echo tracks, genre top, equals, rock. Then subset only the rock songs, and take a sample the same size as there are hip-hop songs. Rock only equals rock only.sample, hop only.shape, 0, random state equals 10. Then we have to concatenate the data frames hop only and rock only. Rock hop bal equals pd.concat, rock only, hop only. Then we have to create the features, labels, and PCA projection for the balanced data frame. Features equals rock hop bal.drop, genre top, track id, axis equals 1. Labels equals rock hop bal, genre top, PCA projection equals PCA.fit transform, scalar.fit transform, features. Redefine the train and test set with the PCA projection from the balanced data. Train features, train labels, test labels equals train test split, PCA projection, labels, random state equals 10. Does balancing our dataset improve model bias? We've now balanced our dataset, but in doing so, we've removed a lot of data points that might have been crucial to training our models. Let's test to see if balancing our data improves model bias towards the rock classification while retaining overall classification performance. Note that we have already reduced the size of our dataset and will go forward without applying any dimensionality reduction. In practice, we would consider dimensionality reduction more rigorously when dealing with vastly large datasets and when computation times become prohibitively large. First, train our decision tree on the balanced data. Then train our logistic regression on the balanced data. Finally, compare the models. Success. Balancing our data has removed bias towards the more prevalent class. To get a good sense of how well our models are actually performing, we can apply what's called cross-validation, CV. This step allows us to compare models in a more rigorous fashion. Since the way our data is split into train and test sets can impact model performance, CV attempts to split the data multiple ways and test the model on each of the splits. Although there are many different CV methods, all with their own advantages and disadvantages, we will use what's known as k-fold CV here. K-fold first splits the data into k different, equally sized subsets. Then, it iteratively uses each subset as a test set while using the remainder of the data as train sets. Finally, we can then aggregate the results from each fold for a final model performance score. Using cross-validation to evaluate our models. Set up our k-fold cross-validation. Train our models using k-fold CV. Print the mean of each array scores. Click the link on description that will open page like this. Here click on song by genre. It consists of dataset and IPYNB file. Happy coding! Please subscribe to my channel. Your single subscription will make my day. Thanks for watching. See you in the next video.